In this video, we'll be calculating future value. This is an application of a finite geometric series. And the question that we'll investigate is this. Suppose an investment of $500 is made each month into an account that earns 6% annual interest compounded monthly. Assume interest on the account is calculated first each month, and then the monthly payment is credited. The questions that we'll go through are, we'll let B sub n represent the balance after the nth payment, or after the nth month. And let's define B sub 0 to be 0 so that we're starting with a 0 initial balance. Let's write the first 5 balances in the account, that is the values B sub 0 through B sub 4. We'll write a recursive definition for the sequence of monthly balances. Let's find out how many years it will take to reach a balance of $1 million and show those steps that are required to solve for the value of n, and then we'll just compute the balance after 10 years. Okay, so let's just sort of orient ourselves here with the idea of an infinite geometric series to begin with, a pretty familiar topic in a Calc 2 class. Infinite geometric series can be written in this form where A is the initial term, R is the common ratio, and if we are adding terms continually forever, we call that an infinite geometric series. What I have written below it is an expression for a finite geometric series, and of course being finite it ends, and this one has n terms. It starts with little n equal 1 and goes to capital N or big N, so that means n terms, and of course if you plug in little n you get plug in little n equal to 1, you'll get 1 minus 1 on that first term, and so you get the first term as A. When you plug in 2, your second term has a factor of r, that common ratio r. Third term has a 2. When you plug in 3, that's 3 minus 1 gives you a 2 for the exponent, and it continues until you finally plug in the last term, capital N, and you have a power n minus 1 there. So this is a finite number of terms. So we could call this sum S sub big N and call this the nth partial sum of the infinite series. So in studying the infinite series, you also need to understand a formula for the sum of the finite series. The finite series is what we call the nth partial sum. Okay, so we can develop from this a formula that'll be convenient to compute the nth partial sum, and then that's what we'll use as a fundamental piece of answering that bank problem that we just read through. Because this is a finite series, I know that each of these are definitely numbers that there's no question of convergence, or that's not an issue here because there's a finite number of terms. So let's proceed in this way, and what I'll do is because it's an equation that I have written here, I can multiply both sides by the same thing and it's still equal. So what I'll do is I'll multiply both sides by the common ratio r. So if we multiply both sides by r, we could begin like that, and then distributing this r to each one of the terms. Each of these terms will get an extra factor of r, which increases the power. Now the term that occurs right before this one would have been n minus 2, and when you multiply that extra factor of r, you're going to get r to the n minus 1. So we get this a times r to the n minus 1 that comes from the term right before this one, and then plus, and then the last term is when you multiply r times this term, you get a times r to the power capital N. Multiply times each term and it produces an expression like that. Now what can we do with this? Well, what we can do is this. Let me move this middle equation out of the way. And now let's consider what happens if we take the equation on the top and subtract this equation on the bottom, because these are equal amounts on both sides of this equation. We'll subtract equal amounts from equal amounts. We'll get an equation that represents equal amounts. I mean S sub n minus r S sub n, taking this side minus this side, and then over on the right hand side, if I start with this and subtract everything here, we'll have a minus nothing to cancel, so we'll just be left with an a, and then a times r minus the a times r, so these guys cancel, and this subtract that, they cancel, and the next term cancels with this term, and all these terms will cancel. This term will cancel with that term, because you're taking this term and subtracting an identical term, so they cancel, but then finally you're subtracting this last term that isn't going to cancel, so we'll just have minus a times r to the power n. What I could do with this now is, on the left hand side, I've got this factor of s sub n that I can factor out. We can factor out the a on the right side, and then we can divide by this factor of 1 minus r. Okay, so this is a formula for the sum of the first n terms of a geometric series. We could also call this the nth partial sum. So to recap, for a geometric series with first term a and common ratio r, the nth partial sum can be expressed or calculated with this formula. Let's consider a special case if the absolute value of r is less than 1. Think about the limit as n goes to infinity of the nth partial sum. That limit is a over 1 minus r in the special case that the r, the common ratio, is less than 1 in absolute value, some fraction between minus 1 and 1, because in that case, as n gets bigger and bigger, and you say a fraction of a fraction of a fraction, like a half of a half of a half, as the n increases to infinity, this term goes to 0, and what you're left with is just an a on top and 1 minus r that don't change as n goes to infinity. So this is the sum of the infinite series only in the case that the absolute value of r is less than 1. In that case, the infinite series converges, and it converges to this value a over 1 minus r. But in the case that the r value is not less than 1 in absolute value, we can still compute a finite series. The infinite series will diverge, but the finite series can be computed with that nth partial sum. But the finite series can be computed with the formula for the nth partial sum, which we had just derived. Now, if I say the sum of the first n terms, I'm using a capital N because I'm using my index as a lowercase n. So I needed to use some other variable to indicate the number of terms that was distinct from the letter lowercase n. Somebody else might write this like, with a different index. Like maybe we could go k equal 1 to lowercase n, a r to the k minus 1, and then it would be a to the 1 minus r to the n over 1 minus r. So this is a formula for n terms. A formula for n terms, if I used a lowercase n, those are the first n terms of this series that's written in this way. So finally, this is the formula that I'm going to use throughout this example of these savings, making deposits, and earning interest, and calculating a future value. So let's look back at the question, because I've definitely forgotten it after all that. Suppose an investment of $500 is made each month into an account that earns 6% annual interest compounded monthly. Assume interest on the account is calculated first each month, and then the monthly payment is credited. B sub n represents the balance after the nth payment and the nth month, and B sub 0 is 0. Write the first 5 balances in the account from B0 through B4. Okay, we've got a $500 deposit each month, annual interest of 6%, and what I'll do with that is I need to get the monthly interest. So this is a expression for the monthly growth rate. It's growing at 0.5% each month. We know that the initial balance was 0. Let's look at the balance after each month and after each payment. So after the first payment, we'll just have $500. And after the second payment, we'll have interest, 1 month of interest on that $500 plus a $500 payment at the end of the month. So 5% growth on the money that was there previously plus another $500. This is 502.50. So here's where we are so far. After 2 months, $1,002.50. At the end of the third month, after 3 payments have been made, we will have made that third payment and we will be earning interest on all those previous amounts. We could just calculate it this way for right now. I'm going to explore other ways to do this as we move along. But I'll take the previous month's balance and say whatever was in the account in the previous month, you're going to earn 5% monthly growth on that amount. And so that's I'm multiplying by 1.005. I should have said that before. It's because it's growing each month by 0.5%. It's growing by this 0.5%. So we need to get 100.5%, or we need to multiply by 1.005 in order to take the original amount plus the 0.5% to get those added together, right? So it causes it to increase by 0.5%. The previous month will increase by 0.5% and be added, and then we will add that third payment of $500. So this is $1,007.51. So we're at 1507.51. And then the fourth month, at the end of the fourth month, after 4 payments, we'll take the previous amount, get 5% growth, and add another $500. So $500 added to the 5% interest on the previous amount. And so that's the sequence of balances, the first 5 balances. The first 5 balances are 0 and then 500, 1002, 1507, and 2015. This answers part A of the question, to find the first 5 balances. Let's move on to part B, which is to write a recursive definition for the sequence. What I want to emphasize here is that a recursive definition always has to have 2 parts. It has to have an initial starting value, and then it has to have some formula that tells you future values based on original values. But don't forget that initial start value, sometimes called the seed. It's not a complete recursive definition without those 2 parts, and those are often missed on exams. The first part, people always forget that first part, so pay attention to that. 2 parts in your answer for a recursive definition. The first part would be the starting value, which we could take to be 0. And then when you write the recursive definition, you're writing any balance based on a previous, or any value based on a previous value in a recursive definition. So in this case, it's the nth balance based on a previous balance, and we've developed it by just going through those examples before. The nth balance is based on the n-1 balance. It's $500 plus, let's say, the growth factor 1.005 multiplied by the balance in the previous month. That's a recursive formula then that you could use to generate any balance based on any balance, because we know the initial balance and we know a formula to generate all the balances from that. And so that could be a useful tool to calculate balances, but there are other ways to express the sequence of balances that will be more useful for answering the questions that follow. Because, for example, if you want to know how long it takes until you get $1 million, or how much do you have after 10 years, this would not be a convenient way to do it by hand. It could program it into a computer, which would be fast enough to compute it this way, but it's not the most efficient way. And also there's really important principles here about how the principle grows, little pun, and the principles that I want to get to is the sum of a finite geometric series. So let's see how we can build that in. Basically, to answer part C, it's not going to be convenient to calculate that using the recursive definition, and this is where we can look at the balances as a geometric series. So we'll approach the question like this. We'll say the balance at time 0 was 0, and the balance at time 1, or after 1 month and after 1 payment, that was 500. Okay, so far easy. Let's look at the second month. What we have to do is take the previous month and add 500. I'm putting the payment of 500 first and then taking the previous month and multiplying by 1.005, right? And then the third month, we get that $500 payment, let's say after you get interest on the previous, right? So this is the most current payment that I'm writing first, plus now I'm going to take all the amount that we had before, but rather than computing it, I'm just going to copy what we had because I want you to see the pattern. So that is B2 right there, just copied. So I take the previous month's amount, increase it by 5%, and add a $500 payment on it. And now, just to rewrite this, you'll see a pattern develop. If I distribute this 1.005 times both terms, it'll look like that. Another way to think of it is, you made the most recent payment of $500 that is there at the end of the third month. We've got 5% interest on the payment that was made just in the month before, and then this will actually represent 2 months of 5% increase on that first original payment back from B1. We could continue this for one more month and say there's a $500 payment that is made at the end of the fourth month, or that is made after the interest for the month has already been credited in. So it's 500 plus all of this times another 1.005. So perhaps I could just do it this way. I'll say if we just copied everything on this line, if I just bring that previous month's amount down, multiply it by 1.005, so that you have 5% growth on the amount that we had the month before, and then we add another $500 to the account, this will be the amount in the fourth month. We could check to see that each of these are producing the same thing that we had before. I'll leave that as a exercise for the reader, viewer. Yep. Distributing this. So the balance after 4 months is this finite geometric series with a first term 500, a common ratio of 1.005. So this is a common ratio bigger than 1. This will definitely diverge. The more payments you make, the bigger your balance, of course. We're not going to expect this to add up to anything if you were to add more and more. It's not going to get closer to something. It'll get bigger and bigger and bigger. But we do have a geometric series, and each sum, each of these finite sums, is a number that we can compute, and we can compute with that formula for the nth partial sum. Notice a pattern here that the fourth partial sum ends with a power 3, so we can generalize this and say the balance after n months, after n payments, is 500 plus 500, 1.005 plus, and it would continue up to this last term that has to have a power n minus 1, because that is one less than the number of payments or months. In fact, this is n terms after n payments, but only the first n minus 1 payments actually earn interest. You're getting that last $500 payment that didn't yet earn interest in the nth month. Now, beautifully, we can fit right in here a formula that we can compute this without actually needing to add up n terms, right? We can simplify this as 500 1 minus 1.005 to the nth power over 1 minus 1.005. I'm using this formula for the nth partial sum of a geometric series. Be real careful about the parentheses and the exponent here. This isn't 1 minus r to the n power. It's just r to the n power subtracted from 1. So we could simplify this certainly, and we could rewrite it because we'll have 500 1 minus 1.005 to the nth power. This will be a negative 0.005, and you could just leave it like that, but I want to rewrite it one more time because we have I've done some videos for Math 106, and in the Math 106 class we calculate the future value after a sequence of payments. And this is basically, here we've just done it in the Calc 2, a derivation for that formula in the Math 106, in the Math of Finance. So I'm going to rewrite it just a little bit so that it looks closer to that form. This could be written as 500. I'm going to just multiply top and bottom by a negative, switch the order of the terms. This is 1.005 to the nth power minus 1 over 0.005. So, of course, this will do. This is the same thing. I haven't answered the question yet, but I wanted to pause on that just a minute to talk about the way that we write it in finance is the principal after n payments is whatever the payment is. We have to be careful with the grouping symbols, so to be clear, let's do 1 plus r to the power n minus 1 over r. When we're doing the math for finance, we actually write this r over k, nk minus 1, r over k. This is a frequency per year. And when we write it in this form here, n has to be number of years. The big N is the number of years. So that's just nice to be able to connect this with some formula that is given in the Math 106, in the Finance chapter in Math 106. This formula is given, but we've just gone through the derivation of where that formula comes from, more or less, and I'll leave it at that because I want to get back to what we're supposed to be working on. Let's go back. We'll use this here. We want to know when this balance will reach $1 million, and this is a quick way to get to that answer. We can solve for n. Multiplying both sides by 0.005, that gives me 5,000, and then dividing by 500. So I get that. Add the 1 over. Take an ln on both sides. This is about 480.78, and that was months because n in the way that I had developed that formula, though n represented months. So that's 480 months. So how long is that? If we divide by 12, we can get the number of years. That's about 40 years. So you hit $1 million after 40 years of making $500 monthly payments with 6% growth. Now let's move on to the last question that I put on there. What's the amount after 10 years? Now we've got to be careful with this. 10 years is 120 months. So in my formula, I had developed the amount after n months, or n payments. And so I need to use 120 months for the 10-year period. So if it's growing 5% a month for 120 months, $500 each month will produce this value. Simplifies to about $81,939.67. And so that's the answer, but we could check this on the computer in a couple of different ways. First thing we could do is, I found this website that's pretty useful for this specific question. Calculator.net, future value calculator. Let's go take a look at that website. Okay, so here I am on that website. It looks like this when you first start, and number of periods, number of compounding periods. Let's try 120 here. Let's say starting amount was 0. Interest rate per period as a percentage, 0.5, because there were 120 periods, right? And how much were we depositing each period? 500. And then here, this is why this is a good website for exactly this point, because it allows me to switch back and forth between whether the payment is initially made and then interest is earned all through the entire period, from initial payment and interest right away, or is the payment made at the end after each compounding period. And that's the way that I develop the formula. So I'm going to choose that option there. And when I calculate it, yeah, that's exactly the number that we got with our formula. So this website is using that exact formula. And it's kind of nice because it gives me a picture here of the increasing balance reaching about $81,000, almost $82,000 after 10 years. These are just the increasing principal amounts that have been paid. So you can see how the principal and interest are, well, actually, this is the total future value. And so the principal is what you're actually paying without any interest. So you can see how the amounts diverge, how the balance begins to increase with this interest as the interest continues to grow. Just to emphasize that, let me just switch it to maybe 240 so that it's 20 years. So this is really pretty neat. This might be something to come back and look at with for another video, but how I'm making steady increases here in the principal, but the interest is growing exponentially, and so my future value is growing exponentially over time. We found out that it took 480 months to hit $1 million. We could check that as well. 480 periods. So it was just over 480 months. So there's, yeah, that's pretty fascinating, right? To see how steady payments are just going to grow to a total of $250,000 of money invested. Yeah, that makes sense. If I take $500 times 480 payments, I'm going to have $240,000. So actually, you're just below the 250. $240,000 actually invested. That's only $250,000 invested. But what's the actual value? It's up at $1 million because of all of that interest over that 40-year period. We came up with an answer that was like 480, what did we get? 480.8 months. So it was in the 481st that you would go over $1 million. So 481. And we're just over $1 million. So yeah, that's it. Oh yeah, that's kind of nice too. Right there, you can see how much of the total balance comes from the periodic deposits and how much actually comes from interest. Yeah, pretty neat. Yeah, we can scroll through the increasing balances. Those are the balances that I generated. B0, B1, B2, B3, and B4 that we had calculated. They're just using a different counting scale here. I called that 0. But otherwise, I'm getting the same values as we see here. So, nice. All right, that's the end of the video. Hopefully it was interesting and helpful. Okay, so maybe not actually the end of the video. I thought about a few other things to say. I went to try this on a couple of other sites. For example, this one comes up real quick if you try Google search. The trouble with this, first of all, is that you couldn't put an initial amount of 0. You could put an initial amount of 1, but it wouldn't take 0. So you'd have to start with an initial amount of 500, monthly deposits of 500. Let's go annual interest compounded monthly 6%, 10 years, calculate, and I get 82,000. Well, that's exactly what you get if you do 121 months with our formula. So that works pretty well. But then if you go to another website that comes up real early in the Google search, NerdWallet, sounds pretty good. I'll try this one. Savings calculator. We can enter in a starting balance of 0 for this one. Monthly contributions of 500. Time to grow, we can go 10 in years or we can put it in months. But if I go 10 years 6% and calculate, I get 82. Now, how come that's 82 when 82,000 when I calculated 81,000? And I finally got to the root of the difference here. I tried to check some of these calculations in Excel, and I realized where that number on NerdWallet was coming up. It's right here, and it's a difference as to whether we're taking money that's already in the account and earning interest on that money and then adding in another payment. Basically just the difference between whether you make a payment at the start of the month and then earn interest that month, or whether you earn interest for the month and then make a payment at the end of the month. Just that little distinction there. It's very subtle, and it leads over time to bigger and bigger differences. The way that I developed the formula was essentially the way that if you did this in Excel, you're assuming payments at the end of the month that don't earn any interest for that month. And so putting in Excel, the calculation looks like this. Future value, this 0.005 is the per period growth rate. I'm looking at 120 periods, $500. I have nothing for the, it's an optional amount. I could just leave 0. That was the starting amount. And then this type 0 means payments at the end of the month. And then only difference is if you put a 1 here, you'll assume payments at the start of the month that then earn interest that month. So this is the same amount, 5% growth per period, 120 periods, $500 payment each period, but make payments at the beginning of the month and earn interest over that month. And you actually have a little bit more in that calculation. So that might be something like, as you can see, when I checked a different website, see if I got the same answer. I didn't get the same answer because there's a slight different assumption in the timing of the payments and the interest. So yeah, be on the lookout for that. Okay, I think I'll stop really there this time. That's the end of the video.